Yeah, we want to talk about the practice of mathematics. Every discipline has rituals, has habits, has practices that it does. Mathematics is no different. So we're going to talk about things that are specific to mathematics. So yeah, what do mathematicians do? How do they do it? What practices do they regularly use? That's primarily the topic of this conversation today. And I want to talk about, I'm going to talk about 5 different broad categories. I have something we call horizontal generalization and vertical generalization. Generalization is big in mathematics. Techniques for problem solving. A big one is making a hard problem simpler, solving it, and then adding complexity. Another technique for problem solving is finding a general formula by looking at individual cases first, then seeing if it's true for all cases or deciding what cases it's true for and for what cases it's not true. We'll look at an example a little later. Using multiple ways to solve the same problem, that's big. Using one area of mathematics in a different area of mathematics, and using mathematics to solve problems outside of mathematics. So we're just going to go through these 5 one at a time and see what they're specifically about. Okay, so the role of generalization in mathematics. So we are generalizing a mathematical result from one situation to another situation. If a technique works in one situation, maybe it'll work in another situation. And this is what I call horizontal generalization. Nobody else calls it that. That's just me. I made it up. Okay, so here's a common problem that you would find in your high school algebra course. We have this quadratic formula, quadratic equation. We want to know, find the values of x that make x squared minus 3x minus 10 equal to 0. Well, fortunately for us, this factors rather nicely, at least I think it does, yeah, as x minus 5 times x plus 2. And everybody knows that if you have 2 quantities equal to 0, then you can set each one of them equal to 0. So if I set x minus 5 equal to 0, that'll give me an x value of 5. And if I set x plus 2 equal to 0, that'll give me an x value of minus 2. These are the 2 values of x, which plugged in here will give me a 0. So that's a very common thing we do in high school algebra. We have other ways of solving quadratic equations using the quadratic formula, which I'm sure everyone in our audience today has memorized and will use it forever. Yeah. Okay. But factoring, that's kind of nice. So how could we use this idea in other situations? Well, you don't have to go very far in mathematics before you might run into some other situations where you can use this same technique. Now here we have the same kind of equation we had before, only instead of x squared and x, we have x to the 4th and x squared. And it happens that you can do the same thing we did before, factor it and solve for x squared and then find out the values of x. Or here's another one more complicated. Instead of an x squared and an x, we have sine of x. So we can use the same technique there. Or how about an exponential function? Here we have, well, this is really 5x squared, and you can use the same technique there also. So you can use the same technique in other different looking math situations. Let's see, here's one that is, how about a nice word problem? I know you all love word problems. So a diver jumps directly upward from a diving board, and it's 32 feet high. My, that looks high to me. I wouldn't want to do that. But anyway, formula that describes the diver's height above the water after t seconds is this thing. So when does the diver hit the water? Well, this is the place where you say, I got to set this equation equal to 0 and find the values of t that make that 0. Again, this happens to be factorable. I can factor it and I can use the same technique we had before. So that's one technique that has lots of applications horizontally across mathematics. Okay, so one important part of mathematics is the ability to recognize patterns and use knowledge obtained from solving one type of a problem to solve a problem that looks a little bit different, or sometimes more than a little bit different. This is an essential part of the ritual or practices of mathematics, the ability to recognize patterns and to employ techniques used on some problems to think about how to solve other problems that look slightly different or maybe even very different. All right, let's talk about something I call vertical generalization. This is generalizing from several different situations by recognizing what is common to those situations and then forming a general principle that applies to all of those situations. Okay, that may be kind of fuzzy to you, but let's give some examples. Okay, here are three sets of very different looking mathematical objects that have some common properties. The set of real numbers has certain properties for addition: the associative property, the commutative property, the additive identity, and an additive inverse. But the set of vectors and matrices with real number entries has exactly the same properties for addition. And the set of polynomials with real number coefficients also has the same properties for addition. So three different mathematical objects that have the same properties. So, and there may be other mathematical entities that also have these same properties of addition. Addition might look different here than it does here, than it does here, but we call them addition. So looking at these different mathematical entities helped mathematicians to say, we should give a name to any mathematical entity that satisfies these properties. We'll call such a mathematical entity a group. And furthermore, if any theorems about groups are proved, and there are a lot of them, then those theorems would apply to all of those different mathematical entities. It applied to the real numbers, it applied to vectors, it applied to polynomials. And if mathematicians discover or invent other mathematical entities that satisfy these same properties, then these new entities will also be called groups. And any theorems that have been proven about groups will apply to these new entities. And here's the process. I don't know if you can read this or not, but noticing properties that are common to multiple mathematical entities, creating a name for those kinds of entities, proving theorems about those structures, applying those theorems to any new entities that satisfy those properties. This is central to what mathematicians do and is part of their practice, their habits, their disciplines. All right, now we're going to talk about techniques for problem solving. And here's one of my favorite, starts simple and gets hard really quickly problem. Okay, so a common technique is you have a hard problem that you want to solve. Mathematicians will say, let's start with a simpler version of this problem and let's solve that one. And then we'll see if we can add some of the complexity. So here's an example. Population studies. It seems reasonable that with constant birth and death rates, the rate of change of the population at any point in time is proportional to the population at that point in time. It makes sense. The more people there are, then the more offspring, the more births that we tend to have. And, you know, if you give enough population, the more deaths we're going to have. So this, get ready. There's a differential equation coming up. So grab on to the side of your chair. This results in this differential equation. The derivative of p with respect to t is equal to k times p. What is k? K is the birth rate minus the death rate for whatever population you're talking about. P represents the population at a point in time. And the derivative of p with respect to t represents the rate of change of the population at time. So I really have p left parenthesis t right parenthesis to indicate that p is a function of time, and the same thing over here. Now, this differential equation has, well, for me, I would call this a relatively simple solution. Some folks might be put off by what that thing is, but this differential equation has a relatively simple solution. C is the population at a specific point in time, usually at the beginning of the time, like the number of beavers in the pond at the time we started to study their population. So yeah, that's nice. That worked out nice, but hold on here. What if the birth rate and the death rates are not constant? What if the death rate's constant, and we'll call that d sub 0, but the birth rate is decreasing as the population grows. There might be lots of reasons for that. Lack of resources to sustain a much larger population, or in the case of the American middle class, we decided to limit the number of children we have so we can give them education and nice weddings and such like that. Okay, well then the birth rate might be represented by, this is a decreasing linear function right there. This is a reasonable assumption if we think about the restrictions on population, like resources such as food and space. When you're talking about animals on an island, for example, that's a biggie, as well as predators. Okay, then the rate of change of the population at any point is, well, here it says it in words. Here it says in a nice differential equation. So here's the birth rate. Here's the death rate. Now instead of a K, we have this more complicated looking thing. And it results in a much more complicated looking solution. And this is a logistic equation, has lots of applications, math, biology, chemistry. I mean, I'm thinking about a titration curve as I look at this sort of thing. And M and K are expressions that involve these constants that we started with, and where P sub 0 is the population at the beginning of the study. Further information about M, it is the limiting capacity. So if you are studying a population and you notice that when it gets to a certain value of, when it gets to a certain point, the population doesn't grow anymore, maybe it declines, who knows? Okay, so yeah, this makes, I added just these simple looking constants here and got a much more complicated solution. That should frighten just about any student in differential equations, I think. In fact, when we went in differential equations from here to here, it took 2 pages of derivations in the textbook. So just saying. Okay, and then of course we can add more complexity. What if the death rate is not constant? Maybe it's increasing over time. Maybe it's decreasing over time. Or maybe the birth rate is decreasing, but it has a different formula than what we had earlier. Or maybe the birth rate is increasing. Or maybe the number of males is much larger than the number of females. How would that affect the change in population? Or maybe the number of females is much larger than the number of males. How would that affect the rate of change of the population? So all sorts of complicated features. I remember a class, we used to teach a mathematical modeling class. And so some of the students, I would assign them to, okay, think about this. So come up with a solution, think about this, come up with a solution, think about one of these, come up with a solution. That was fun. It says it's scary, but that's not true, it's fun. Okay, other factors to consider. Let's see, move that over. How do we account for predators or prey when dealing with animals in the wild? Or how do we account for harvesting a population? What does that mean? Well, deer hunting season or fishing season, those would be examples of harvesting a population. Any and all of these can result in much more complicated differential equations and their solutions. So one thing mathematicians do is to try to solve a hard problem by first making it simpler and then adding other factors to see how that changes. I've been reading a book called The Song of the Dodo. It's about island biogeography, bioecology. And about halfway through the book, there's a set of differential equations that look fairly complicated. And I'm guessing that their solution is complicated. It's talking about the population versus availability of resources, availability of prey and predators and such like that. So differential equations rule, just saying. Okay, how about another problem solving technique? Well, finding a general formula by looking at individual cases first. Okay, so I want to go to my camera here. There we go. Oh, I guess I should go back to the what the PowerPoint slide said. Oops, not that one. PowerPoint slide said. I kind of took us off here. Okay, if we draw a number of chords in a circle, how many sections have we divided the circle into? There's the problem. You can see this problem in elementary math books. You can see it in high school books, college books, graduate studies, because this is a really interesting problem. Now, I'm going to work on this problem by, first of all, saying I'm going to work on chords that only go through the center of the circle. So I'm really looking at a fairly simple example. So there's the first chord, goes from one point of the circle to another point of the circle. That's a chord. And I divided the circle into two regions, 1, 2. So one chord, two regions. And now I'm going to be quite deliberate about my next chord. So now I have two chords, one chord, two chords, and now I have four regions, 1, 2, 3, 4. And now I'm going to try another chord. Again, I'm being pretty deliberate here. So now I've got three chords. How many regions do I have? 1, 2, 3, 4, 5, 6. Three chords, 6 regions. How about another chord? There's chord number 4. 1, 2, 3, 8 regions. So it's not too hard to see that if I had n chords, I might have 2 n regions. And that's for the special case where all my chords are going through the center. But of course, you can get something much more complicated. How about if I just use any old chords willy-nilly? Will I always be able to come up with a formula? And if you study this problem hard enough and long enough, you'll find out that it's not as simple as n chords gives us, 2 n regions. And there's some problems which up until you get 6 chords, things work through the first 5 chords, and then suddenly, oh darn, doesn't work with the 6th one. And mathematicians have studied this problem long enough that they know that the maximum number of regions formed when endpoints on a circle are joined is, there you go, a nice 4th degree polynomial. You couldn't ask for anything better. Who in the world came up with that? Let's see, I've got a number of pages here from the National Council of Teachers of Mathematics, if anybody wants to read how they came up with this. I'm wondering about that. Okay, so there's an example, I think, of a place where we look at some individual cases and try to come up with a formula, or we look at the individual cases and get far enough that we see, okay, it worked for these, but it didn't work for this one. So now we have some restrictions on it. That's a very common technique. Okay, using multiple ways to solve the same problem. All of you who've gone through high school geometry or high school algebra have had to do this kind of thing, whether you remember it or not. Find the maximum value of y where y is governed by that quadratic equation. Well, if you know enough about quadratic functions, their graphs are parabolas, and you can be clever enough to graph that without too much difficulty, plot a whole bunch of points, or you could use your graphing calculator, or a tried and true mathematical technique is guess and check, or you can try to factor it and use symmetry. Use symmetry to find out where the maximum is, or you can use calculus. You can use calculus on this thing. There's lots of different things you can do. There's multiple ways of solving the same problem. Here's another example. I actually drew this up ahead of time. And I know you all love these kinds of problems. 2 ships leave a dock at the same time. One sails northeast at a rate of 8.5 miles an hour, and the other one sails east at a rate of 10 miles an hour. How far apart are they at the end of 2 hours? Well, I drew a little picture here that might help. Here it is. So one's going east. After 2 hours, it's gone 20 miles. The other one's going northeast, I assume at a exactly northeast, 45-degree angle. And here's where they are 2 hours. So your goal is to find that. And there's all sorts of ways of doing that. I suggested one way by, dropping an altitude to get 2 right triangles, and you can proceed to find any of these objects. I can find this, and therefore I could find this, and I could find this. Eventually I might be able to find D. That's one way to do it. Another way to do it is to put the problem on a grid, some graph paper, and actually estimate it. There are other ways. You could be more sophisticated and use some of the laws of sine and cosine to find D directly. So yeah, or you could go out in the yard with a tape measure and try it. So there's lots of different ways of solving that problem. Okay, let me get back here. All right, here is, okay, using one area of mathematics in a different area of mathematics. And again, here's the situation. This is from probability theory. This is actually a problem in early in our probability course, 300 level probability course. An urn contains 10 balls, four are red, 6 are blue. A second urn contains 16 balls and an unknown number of blue balls. A single ball is drawn from each urn. The probability that both balls are the same color is 0.44. Calculate the number of blue balls in the second urn. Okay, there's a lot of words there that can scare people, but let's see if I can make some sense of it. Okay, here's the problem here. So in my first urn, I have 4 red balls, 6 blue balls. And the second urn, I have 16 red balls, and I don't know how many blue balls I have, so I'm going to call them X. And here I've got a total of 10 balls. And here I have a total of 16 plus X balls. I'm told that the probability of both of them being red or both of them being blue, that would be both balls being the same color, is 0.44. And that specs out to, well, this is supposed to be a P here, the probability that I got a red one from the first urn and a red one from the second urn, plus the probability I got a blue one from the first urn and a blue one from the second urn. And then doing the individual probabilities, okay, red from the first urn is 4 out of 10. Red from the second urn is 16 out of 16 plus X. Blue from the first urn, 6 out of 10. Blue from the second urn is X out of 16 plus X. Now you are in algebra land. Once you get to here, we've left probability land, and now we're in solve this equation kind of land. So there's an example of where you have to use algebra to solve a different kind of problem. And that's pretty typical of mathematics. And I'll have to say that algebra is the one thing that pretty much permeates all areas of mathematics. So don't neglect to study your algebra. Okay. Yeah, and a particular concept here. It's very difficult to take any 300 level math class without using concepts from other math classes. Differential equations, we use vector calculus, we use linear algebra. So there's another example there. Okay, I'm going to close this with a video from YouTube. Multiple proofs of the same theorem. This is ubiquitous in mathematics. You might have one theorem and there's lots of different proofs of that theorem. And I'm going to try to bring up this video. There will be about a 3-second advertisement first, but let's see if we can bring this up. It's kind of a cute little cartoon. So hang on here.
This oceanside rainbow is about to become the backdrop for an unforgettable vacation memory.
All right.
What do Euclid, 12-year-old Einstein, and American President James Garfield have in common? They all came up with elegant proofs for the famous Pythagorean theorem, the rule that says for a right triangle, the square of one side plus the square of the other side is equal to the square of the hypotenuse. In other words, a squared plus b squared equals c squared. This statement is one of the most fundamental rules of geometry and the basis for practical applications like constructing stable buildings and triangulating GPS coordinates. The theorem is named for Pythagoras, a Greek philosopher and mathematician in the 6th century BC, but it was known more than 1,000 years earlier. A Babylonian tablet from around 1800 BC lists 15 sets of numbers that satisfy the theorem. Some historians speculate that ancient Egyptian surveyors used one such set of numbers, 3, 4, 5, to make square corners. The theory is that surveyors could stretch a knotted rope with 12 equal segments to form a triangle with sides of length 3, 4, and 5. According to the converse of the Pythagorean theorem, that has to make a right triangle, and therefore a square corner. And the earliest known Indian mathematical texts, written between 800 and 600 BC, state that a rope stretched across the diagonal of a square produces a square twice as large as the original one. That relationship can be derived from the Pythagorean theorem. But how do we know that the theorem is true for every right triangle on a flat surface, not just the ones these mathematicians and surveyors knew about? Because we can prove it. Proofs use existing mathematical rules and logic to demonstrate that a theorem must hold true all the time. One classic proof, often attributed to Pythagoras himself, uses a strategy called proof by rearrangement. Take 4 identical right triangles with side lengths A and B and hypotenuse length C. Arrange them so that their hypotenuses form a tilted square. The area of that square is C squared. Now rearrange the triangles into 2 rectangles, leaving smaller squares on either side. The areas of those squares are A squared and B squared. Here's the key. The total area of the figure didn't change, and the areas of the triangles didn't change. So the empty space in one, C squared, must be equal to the empty space in the other, A squared plus B squared. Another proof comes from a fellow Greek mathematician, Euclid, and was also stumbled upon almost 2,000 years later by 12-year-old Einstein. This proof divides one right triangle into 2 others and uses the principle that if the corresponding angles of 2 triangles are the same, the ratio of their sides is the same too. So for these 3 similar triangles, you can write these expressions for their sides. Next, rearrange the terms. And finally, add the 2 equations together and simplify to get AB squared plus AC squared equals BC squared, or A squared plus B squared equals C squared. Here's one that uses tessellation, a repeating geometric pattern, for a more visual proof. Can you see how it works? Pause the video if you'd like some time to think about it. Here's the answer. The dark gray square is A squared, and the light gray one is B squared. The one outlined in blue is C squared. Each blue outlined square contains the pieces of exactly 1 dark and 1 light gray square, proving the Pythagorean theorem again. And if you'd really like to convince yourself, you could build a turntable with 3 square boxes of equal depth connected to each other around a right triangle. If you fill the largest square with water and spin the turntable, the water from the large square will perfectly fill the 2 smaller ones. The Pythagorean theorem has more than 350 proofs and counting, ranging from brilliant to obscure. Can you add your own to the mix? Did you enjoy this lesson?
Well, there we go. Okay. Now, in addition to the multiple proofs of the same theorem, speaking of the Pythagorean theorem, the Pythagorean theorem is ubiquitous. What does that mean? That means it shows up in the most amazing places, and you can't do very much in life without the Pythagorean theorem. Okay, that's a pretty arrogant statement, but I'm going to go with it. I didn't even have to go very far before I found a couple of interesting research articles. This one's from the European Journal of Ophthalmology, and the title of the article is "The Feasibility Analysis of Calculating Proptosis by Simple Pythagorean Theorem." Okay, there's one. Here's another one from 2015 from the Biological Research for Nursing Journal. And it doesn't say it in the title, but it is an application of the Pythagorean theorem, a theoretical mathematical model to establish blood volume in clinical practice. So there are places where where the Pythagorean theorem is useful besides in just mathematics or surveying. Okay, that is it for my talk. So now we are open for some questions or comments.
So we can do questions in the comments, or if there's not that many of us, we might just be able to unmute ourselves and ask a question. I think we can probably make that work. So questions from anybody? I'll make one quick comment while people are thinking. That last video about the Pythagorean theorem mentioned a water wheel to demonstrate that. We've had 2 different Spring Arbor students attempt to build one of those since I've been here. And I say attempt, they built it well enough that they could demonstrate that in class. And then I put it in my office overnight and I come in the morning and I have a big puddle of water underneath the wheel because we've had some difficulty creating watertight versions of that model. But now that we have an engineering department, we might have some better success trying to get one of those watertight.
Well, let me ask a question. I made some claim about how important the logistic equation is. And I said, you know, it has all sorts of applications in math, ecology, and chemistry. I don't know when Tom is doing titration curves, if he knows that those are graphs of logistic equations or not. Any of the rest of you run into those kinds of equations? Ecology, differential equations? No?
I did in your differential equations class.
Yep. That's where we did it. Yep. It was a great day, wasn't it?
It was. I also did it in quantum physics and heat and thermodynamics.
Okay. So other places, physics and engineering. Good.
Early in the pandemic, there was some discussion that the number of cases and or the number of deaths were going to follow a logistic. Of course, some complications have changed that. But I think if you look, I forget, I think it's one of the two, I think it's the number of cases. It almost looks like in certain places, it shows like there's 2 logistics. Like there's one and then it does another.
And another one, yeah.
And then I'll mention that in chemistry, general chemistry 2, we're going to be using the quadratic equation probably on Friday and throughout the rest of the semester.
Wonderful. Nothing better than the quadratic equation. I'm just saying. No equations in organic chemistry, Bruce?
There's a whole area of study in organic chemistry called physical organic chemistry. And that's the part of organic chemistry that I survived and put up with and don't remember very much at all. Things like the Hammond postulate come to mind and kinetic studies. And now that I'm TAing for Dr. Kunzelman, I'm beginning to understand a little bit about how natural logarithms and graphing things that happen give you insight into what's going on that I had, maybe I was taught that, but I don't remember being taught that from that perspective. I think that's a very liberal arts kind of thing to be doing.
Mm-hmm. Yep.
And it's interesting. It's intellectually stimulating.
I'll also throw in there, you mentioned groups.
Yeah.
In chemistry, each molecule belongs to a particular group.
Yep.
And we can understand, I mean, you know groups a lot better than I do. I mean, I have to study really hard when I'm getting ready to talk about this because I don't think about it very often. But when I do teach it, it's remarkable how much you can, for example, tell about a water molecule just by understanding its symmetry, what group it belongs to. We call it C2V. I think you all call the groups by different names.
Yeah, could be. Everybody ready to go get coffee? It looks like maybe that's on the next agenda item.
So, Garnet, I'll ask a question.
Okay.
So you essentially had 5 different practices of mathematicians.
Yeah.
Generalizations, the techniques of hard to simple, one case to many cases, different using mathematics in different areas of math, using it outside of math. Do you think any of these practices apply more generally to people who are not necessarily in math or science related fields? Are there things we can learn from that
Hmm.
to the English major that may be listening or the history
Hmm.
major that may be listening?
Well, I think the role of generalization is broader than just mathematics. Yeah, often people will look at, okay, I think this might be true, so let me just look at some examples and see if it's true. And I think that occurs in politics also. We tend to say, oh, well, this group espouses this because here we've seen the policies they've come forward with. Now, we've seen a lot of crossover between Democrats and Republicans in recent years. When the Republicans did something, I go, well, that sounds more like what Democrats would do. And then when the Democrats did, that sounds more like what Republicans. So you can't say, well, this happened 3 times before, therefore it's going to automatically happen again. But it is a way to study it. It's a way to think about it. I just used to drive my teenage children crazy because I'd say, well, you did this and this and this. So of course I'm going to think that you're going to do this over here. They go, oh, that's changed. I don't do that anymore. So generalization, I think, is a real life skill, and being able to understand its strengths and its weaknesses, I think. Yeah. Or being able to appreciate that there's more than one way to solve any given problem. I mean, we're involved with that at the state legislature and the national Congress, trying to think about how to solve a problem. And then there's, different groups have different ideas about how that can be done. I don't think that's strictly a mathematical concept.
So I'm going to get on a soapbox. Do you think it's fair to say then that when we teach students mathematics, it's not simply so that we teach them to be able to factor an equation, but to teach them some of these mathematical practices that they then can use outside of the area of
Oh,
mathematics?
yes, definitely. The old-fashioned idea of studying hard subjects was because it disciplined your mind and broadened your view of the world, and informed you when it came to working within the context of society and culture and politics and religion. I think that's true.
Of the practices of mathematics, which would you say is or are the most important, and which do you find most enjoyable?
Wow. Well, all of them are important. I'm just going to say that. But yeah, I like seeing multiple ways of solving the same problem. When I was a kid, if algebra didn't solve the problem couldn't be solved. But in my undergraduate work, there's such crossover between one area of mathematics and another area of mathematics that I begin to appreciate multiple ways of solving the same problem. In graduate school, I was taking a math ed class, Deborah Ball. Some of you might have heard of Deborah Ball, and Dan Chazen. And, they were presenting a problem. I solved it, of course, the correct way. But some other students took a more intuitive approach and solved it another way. And I just said, wow, that's cool. I didn't even think of that. So I think that's a big thing, being able to appreciate multiple ways of solving the same problem. Yep. They're all quiet.
So the 5 practices you listed are all what I would call good practices. Things we want to do as mathematicians. As somebody who's taught mathematics, I would say a lot of people show up in my math classes with what I would call bad mathematical practices.
Oh, no.
And those can range from things like if you have a plus b squared, trying to distribute a square. So they can be bad mathematical practices, or they can be more general type of things like if you see -2 plus 5, reaching for the calculator to do something like a -2 plus 5 that most people should be able to do in their head, but at the same time, they've conditioned themselves to do arithmetic on a calculator. Even if they don't need to do the arithmetic, they just condition themselves.
Yeah.
So how do we break a bad practice? I mean, can we beat it out? I mean, we can't beat it out of them, but how do we break bad mathematical practices?
Well, that brings two thoughts to mind. I'm teaching a math class for elementary teachers, and one of the cautions you want to give people who are teaching in the lower grades is that you need to be careful how you talk about operations, because they may not, operations involving integers may not translate wonderfully or simply or correctly to operations with rational numbers, with fractions. You have to be careful about how you talk about. I mean, a common way, I have a great granddaughter in first grade. A common way to talk about subtraction is take away. 5 take away 2. Well, how do you talk about 5 take away -2? Okay, so students have to relearn a different way of talking about subtraction when they get to positive and negative integers, because the takeaway concept doesn't work as cleanly there. Another thing I used to do when I taught calculus, I would ask a question. Students would sometimes give you an answer that might have been okay in high school, but it wasn't precise enough or it wasn't specific enough to be good enough in college. And I would simply say that's a great high school answer. Now, in college, we need to be more precise. We need to be more specific. We need to be able to explain what we're doing and why we're doing it. We don't just have a bare naked answer. So, yeah, I'm not going to rail against high schools and the way they teach math, because I don't think it necessarily translates into what students tell you on the first day of calculus in college. But this was a way that I tried to handle it, saying, okay, let's make that more a college level answer.
Did you run into that same problem with students who took AP calculus then that transferred in
Ooh, that's
with
a
that
good
credit
question.
in Calc 2 then?
That's a good question. I don't know. I don't know. I don't remember that. Yeah. Those students tend to be better students, period. So was that you, Seth? Were you one of those people? No, you weren't.
I took AP calculus, but then my teacher the second semester had a baby, so she wasn't there. So the second semester of AP calculus kind of fell apart, so no one could teach it.
Yep. Good question. I haven't thought about that.
You know, with AP calculus students, it's interesting because you can do calculus in a number of ways when you solve certain problems, because there's always more than one way to do something. And so in Calc 2, I'll have 2/3 of the class that will do it very similar to how I taught it first semester. But then the other third of the class may come in with slightly different methods for accomplishing the same thing. And so I'll be teaching something in Calc 2 and they'll be like, hey, can I do it this different way? And so trying to accommodate, sure, you can do it that different way. And every once in a while, I'll do that on the board. And so trying to have two different versions be okay with each other doing it different ways is sometimes an interesting navigational problem in Calc 2. Or even in Calc 1, sometimes the people who have taken AP Calc but not passed the exam will want to do a slightly different way. Like for the definition of derivative, there's two good ways to define the derivative with limits. And depending what book you had as a high schooler or as a college student, you'll have different ways of doing it.
I'm also thinking about implicit differentiation. You always have students who had good high school calculus who want to say, oh, there's an easier way to do that. And I want to tell them that, okay, shut up for one more day. Then I'll let you show us. But today we're going to do it for those who've never done implicit differentiation. And I see that Tom put in here division by 0. What do you want to say about that, Tom?
That was in response to the question about what are bad practices in
Yeah.
mathematics.
Yeah. Yeah.
It's
And
a bad nerd joke, that's all.
when I teach math for elementary students and we're talking about fractions, rational numbers, and talking about a 0 in the denominator, then I try to guide them through a discussion about why that creates problems. It's not like it's illegal or against the laws of mathematics. It's just that it is consistent or it leads to other problems that don't work. So yeah, we mathematicians do that. Don't do this because it leads to inconsistencies or it makes these other rules not work so well. Yeah, we do that.
What's funny is sometimes in science we think about the physical meaning of all this stuff.
Yeah.
So we're okay with dividing by 0. We just say, look, it's just really big. Then we're done.
Right. Yeah. Don't divide by 0, divide by 0.00001. And then you got an idea what that fraction is really about. Yeah. Good point. That's a calculus kind of thing. Yeah. Yep.
I had a teacher in high school who I had it was supposed to be trig and calc, but we spent almost the entire year on trig. And he basically said the reason why is because a lot of calc professors didn't like when they came in doing a bunch of different, like doing it the wrong way. And I didn't know if you guys had any preference or any ways of thinking about that.
Well, my frustration with first semester calculus students, and since you're talking about trig, is that they don't know their trig as well as I think they should know it. Maybe you knew it better because you spent so much time on trig, but they will say, oh, I don't remember trig, or they'll even say, oh, I didn't have that, even though they will say, well, yeah, we had trig, but I don't remember that. And so over the years, one of the things I had to adjust to when I was teaching calculus was to understand that the trig rumbled around there somewhere, but it was way somewhere, a vapor somewhere. And I really had to say, remember in trig when we did this? And then I would go through some trig before I zapped them with the calculus. Yeah. I stupidly thought that when you learn something, you kept it in your head forever. Well, I know that's not true, but trig, come on, trig is like high school math. You gotta have that, right? Yeah, okay, I was wrong.
But also for trig, in terms of the multiple ways of doing things,
Yeah,
there's trig with triangles,
yep,
or there's unit circle trig.
right.
And they're both trig, but they're different approaches to it. And depending upon what approach a student learned, they're going to come to calculus differently.
Yeah.
And I tend to find most students show up to calculus having learned trig with triangles, but putting it on a unit circle, which also uses triangles, is now different. And trying to make the connections between those two areas and say, no, it's really the same thing you learned, just a different viewpoint of it, is a challenge.
Yep.
And again, getting back to the idea that the same math can be described different ways.
Yep.
Yeah, they kind of go off that, having different math techniques. I know in high school, we switched over our math books like halfway through my high school career, and I petitioned to use the old math book, and I finished with the old math book. But everyone who changed the new ones were so lost because all the techniques instantly changed. Like they weren't similar in any way.
Mm-hmm.
So
Yeah, so that's something you have to think about when you're writing a textbook series. I'm not up for that, but you know, in case anybody is.
That's the issue. A lot of times, people will complain about Common Core is because they are doing some of those classic techniques slightly differently. And so the parents will say, I learned this method for
Yeah.
doing it.
Right.
Why are you teaching my kid a different method? And so then there's conflict because, if the method worked for the parent, why not just keep using it? And there might be reasons to use a different method, or just simply for the idea of let's teach them 5 different methods so they know 5 different methods. In and of itself is not a bad thing. But the parents who learned their one way of doing things want to stick to one way of doing things
Mm-hmm.
rather than allowing the option of learning different methods.
Yeah.
It is almost 9:30. I think are we done at 9:30? I don't know.
Oh, gee, I hope so.
So if there are any outstanding last questions people want to ask of Dr. Hauger.
I actually had a question. When you said that you would ask for a more college answer, I guess how I always thought of math and why I liked math was because there was always one right answer.
Right.
So what did you mean by you would want a more college answer rather than high school?
Well, 2 things. One would be show all your steps. I think in high school, many students, they don't show all their steps, and so that's very important. Or being able to write write an answer that explains your answer. Write a sentence that explains your answer. Or being able to justify it by saying, well, here's what I'm drawing on from Trig. Here's my picture. Here's my idea. Just being more specific and more detailed. I remember, let's see, those of you who've had calculus know this, that if the derivative at a particular point on an interval, if the derivative is positive, then that means the original function is increasing. I would get a terrible headache when a student would say, well, it's increasing, it's positive, therefore it's increasing. So you're using the same word, it, to mean 2 different things. And so I would caution them, you need to talk more precisely and more specifically. You can't just throw out any old pronoun and think that I know what you mean. So if you're going to use the word it to mean the derivative, then it can't mean the function. So that came up every time I taught calculus. So the language needs to be precise and detailed. So I might think of some other examples later. If I see you in the hallway, I can give them to you. Yeah. But that was one specific one. They may have let you get by with that in high school because we all knew what you were talking about. But here you need to be more specific, more detailed. Or sometimes students would say, well, to go from here to here, I don't really know why that's true, but I just know it's true. Well, in math, you need to tell me why that's true, or you need to provide some argument. Or I try to, even it's even okay to say, well, I don't know the real algebra or trig that makes that happen, but I tried a bunch of examples and it worked. So I'm going to go with it. Just to be able to explain what you did and why you did it. That's a college level kind of answer that I don't think is always emphasized in high school. I could be wrong. It's been a while since I taught high school.
I appreciate what you said about the language. Sorry, I just joined the meeting. I was at another one. So I appreciate what you said about language because, in all my classes, I feel it must be emphasized. It is statistics. Mm-hmm. It is any research class. It is any leadership class. It is in general the ability of students to speak very clear and build the sentences proper way, and it reflects or relates writing the same way, because people through sometimes I feel that students like through kind of trash to me in their writing, like they assume that they write the way how they speak, and they assume that everything must be understood. So no, I think math is very good area when where students should be taught or required or expected, and these expectations must be very clear, very clear delivered to students, for any subject. So thank you. I appreciate this point.
Thank you, Ina. That was helpful.
Dr. Hauger, thank you for sharing with us today. I appreciated your talk. I want to thank everybody for attending and asking good questions. And I encourage you to attend the rest of the focus talks throughout the rest of today and later this week. So the full schedule is in the app to look up the other talks. But thank you all for joining us this morning.